Welcome everyone. For today's prep, we're going to keep looking at improper integrals, and we're going to look at a few other cases. So far, we've looked at a couple examples where we've calculated improper integrals of this form, where we're integrating from some constant a to infinity. So for these types of integrals, the interval we're considering, it's an infinite interval, and it's going from a to positive infinity. And the way we've seen how to handle this is, again, infinity is not a number, so we gotta be careful on how we handle that infinity. So our idea is we replace that with an actual number, so we're just going to call it b, and then we let that number b get larger and larger positive. So we calculate the limit as b goes to infinity. All right, so sometimes we call these like right-hand improper integrals, and that's because if we look at the graph, we're starting at some a value here, and then we're looking at this kind of right-hand region that sits under our curve. And for non-negative functions, what this improper integral is really doing is it's calculating the area for that shaded region. All right, well, what about the other side? How are we going to handle that? So sometimes we call these ones left-hand improper integrals because we're looking kind of at the left side region of our graph over here. And these occur when we're attempting to integrate over an interval negative infinity to some number b. All right, so how do we handle these? Very similar. So that minus infinity, not an actual number. So the way we deal with infinity, or minus infinity in this case, is we have to approach it. So we change our lower limit to some number a. So we're going to leave it as a variable. So we'll just say a. And then we're going to let that number a get larger and larger negative. So we're going to calculate the limit as a approaches minus infinity. So again, this is the correct way to deal with infinity. We can't just plug it in. We have to kind of approach it. So you want to think of infinity and minus infinity more of like a destination rather than an actual number. So we have to kind of sneak up on it. All right, so if we calculate an integral of this form from minus infinity to b, what we're really doing is we're looking at the kind of the left side of our graph. So we're attempting to calculate this area here. And there's one other type, and that is an improper integral of the form minus infinity to infinity. So how do we calculate something like this? Well, we split it up. So we pick a number, some x value in the middle. So we've got the entire x-axis. If we're looking at the graph here, we've got the entire x-axis that we're integrating over. So the interval in this case is going all the way from minus infinity to positive infinity. So we're looking at the entire x-axis. So how we actually calculate this is we split it up into two of those previous types. So we pick some number in the middle. Usually we pick x equals 0, but you don't have to. You could pick something else. Usually 0 is nice though, so we kind of make a slice right in the middle there, and then we calculate the left and the right sides. So that's our idea. Put a nice slice right down the middle, and then we break it up into two solvable quantities. So we can calculate this side, and then we can separately calculate this side. All right, and the key thing here is both of those improper integrals, the left side and the right side, both of them have to be convergent. So we need to be able to calculate this integral and actually get a number, and then we have to be able to calculate the other one and get an actual number. And then we just add those two results together. So again, we need both. So if one or both of our kind of one-sided improper integrals are divergent, then this entire thing would diverge. So if one or both of those diverge, then our entire improper integral is going to diverge. And that makes sense. Because let's say we're integrating and we find that the right side area is infinite. Well, if this side has infinite area, then when we add on, even if the other side has a finite area, we're still adding it on to something that is infinite. So we're going to have an infinite area then. So we need both of these sides to kind of behave for us. So we're going to try an example. And there are some important limits at infinity. So we'll see, this is kind of review from Calc 1. We dealt with limits at infinity. We'll go through these in class. But the one I want to keep in mind is, for the example we're going to look at, is this one for inverse tangent. So this is kind of a special one. The limit as x approaches infinity of inverse tan is pi over 2. And the limit as x approaches minus infinity of arctan is negative pi over 2. So we're going to keep these in mind for our example. So we're going to look at example 3. So we've got this interval, minus infinity to infinity. And we're attempting to integrate this function 1 over 1 plus x squared, essentially over the entire x-axis. And we want to find if this thing is convergent or divergent. So how are we going to do this? Well, we've got one of these intervals where we're going over the entire x-axis. So we want to pick some finite number, pick some number in the middle, and we're going to split it apart at that number. So, like I said, usually 0 is a good one to do. So we're going to split this at 0. So we're going to calculate the integral from 0 to infinity of our function. And we'll see what we get. And then if we get a finite number, we'll go on and we'll do the other one. So let's write down our other improper integral. So we'll do the improper integral from minus infinity to 0 of the same function. And we're going to calculate these separately. So let's start with our first one, kind of what we're used to here. All right, so we got to do something with that infinity. So our strategy is peel it off the integral sign, and we turn this into a limit. So we're going to do the limit as b approaches infinity of the integral 0 to b. And our function here is 1 over 1 plus x squared. All right, so that's our first step. When we're dealing with these improper integrals, we change that infinity into a limit. And what we have left then is this definite integral. So we're just going to calculate this definite integral just like we would normally. So we've learned all these integration techniques. This one turns out to be a nice basic antiderivative, and kind of spoiled it with with the mention of that special form. We've also seen this format with our partial fraction integrals. So this is one of the ones we should know. So this integral is, or the antiderivative is arctan, inverse tan. All right, so we're calculating that definite integral. Every step of the way, we're going to write our limit sign because we still have to calculate the limit. Got inverse tan, and then we'll evaluate this from x equals 0 to x equals b. Let's plug in. So when we plug in, again, still, we haven't done the limit yet, so we still got to keep writing that limit sign. And then when we evaluate, we get inverse tan of b minus inverse tan of 0. And we're calculating this entire thing. We're going to calculate the limit of this entire thing. All right, so inverse tan of 0 is just a constant, and it's actually equal to 0. And then the limit of inverse tan of b, again, this is b here. We're doing the limit as b goes to infinity, and this is one of our special forms. So this is one of those ones to kind of have memorized. So the limit of inverse tan as the term inside the inverse tan function goes to infinity is pi over 2. So we end up, when we calculate this, we get pi over 2 from the inverse tan of b, and then inverse tan of 0 is just 0. So we get pi over 2 minus 0, which is just pi over 2. All right, so what we found is that kind of this right portion of our improper integral is convergent. All right. So this gives us the go-ahead, gives us the green light here to say, well, let's look at the other one then. So if we had found that this was divergent, done. We're done. We don't even have to worry about the left-hand side. Nothing the left-hand side could do could make this then, this entire thing convergent. So, but the fact that we got this convergent, now we're ready to go on and check the other side. All right, so let's try this. So first thing we got to do is we got to deal with that infinity, that minus infinity. So just like in the previous example, we're going to rewrite this as a limit. And we'll do our limit from a to 0. And we're going to let a approach minus infinity. All right, so it doesn't really matter what variable you're using here. Kind of just use an a and b, just because that's how we normally write the general form of indefinite integral. The only thing you can't use is the variable that's in your actual function here. So our function has variable x. We just can't use x because x, we're already using x. So we got to use something else. So I like a and b. These are kind of easy to read. I know the textbook uses t. T's, in my opinion, kind of get sloppy, at least for me. So I use a and b. The only thing, you just can't use x or whatever the variable is. So for this minus infinity, I'm going to use a. And still the same function. And we're still going to take the same approach. We're going to deal with that definite integral first. So let's get this definite integral first. And all the steps along the way, we're still going to have that limit sign in front because we deal with the limit part. That's kind of like the very end. All right, so this is still the same antiderivative. So that part's kind of nice. Still going to evaluate the same way. Top number goes in first. So when we do that, we get inverse tan of 0 minus inverse tan of a. And now we're ready to calculate the limit. Sometimes you might want to simplify this down. There might be a little bit of extra work, but in this case, we can just do it. So inverse tan of 0 is just a constant, so that just approaches whatever that is. We know it's 0. Then we're subtracting. And let's figure out what the limit of inverse tan of a is as a goes to minus infinity. And if we just pop back up, let's look at that special form. When the term inside our inverse tan function is approaching minus infinity, the limit is negative pi over 2. All right, so we're going to use that. And so if we simplify, we end up with positive pi over 2. And that means this one is also convergent. All right, so both of the improper integrals, both of the sides here are convergent. So that gives us the green light now to add them together to get our total improper integral. So this means the improper integral from minus infinity to positive infinity of the function 1 over 1 plus x squared, well, this is actually just equal to the integral from minus infinity to 0 of the function plus the other one, 0 to infinity. Kind of one of our usual definite integral type properties. The only thing is it's not so nice because we have these infinities, so we kind of have to be a little careful here. But what we found is we found a nice number for each of these. So because we got an actual number, we can just add the two results. So we end up with pi over 2 plus pi over 2 and pi. All right, so what did we do? Oh, I don't even have the graph. Well, the graph is here. Let's just go back. So this is the graph. So this is what 1 over 1 plus x squared looks like. So essentially what we did, we found the area of the right-hand side, which was pi over 2, found the area of the left-hand side, pi over 2, and then we just added them together and got the total area. All right, so we're going to try a couple more of these examples in class, and we'll look at some examples where the limits are actually a little bit more complicated. So right now everything's been kind of basic limits at infinity type things. We'll start to look at ones where maybe we got to use some of our other limit techniques like L'Hopital's rule. So we'll see you then. Bye-bye.